Some of you know. Can you hear me? Well, I'll try to speak up as much as I can. My name is Despina Moschou. I'm currently at the University of Lab, and I just moved over there from Southampton this month. And I'm currently the Prize Fellows class lecturer there. And interestingly, I've been working in a technology that could be of interest to you, which is called Lab-on-PCB technology for the past 6 years. I happened to meet Steve earlier and a lot of the guys in your industry, and they seem also to be very interested. So we thought it's a good idea to inform you about what we're doing and see if we could have some synergies together. So, briefly, I will talk about what it is that we do and why people around the world are looking for it research-wise. So, what is microfluidics? What is lab-on-chip technology? And why would you want to use PCBs in that? And why are people starting to look into that closer? So briefly, what are microfluidics and why do we need them? I guess most of you are familiar with microelectronics. So microelectronics are basically electronic circuits in a small scale. This is great and it has worked for the past 30 to 40 years, but when we are trying to do analysis in liquid samples, as is the case in biomedical applications, let's say, for diagnosis, blood diagnosis or urine diagnosis, or environmental applications, in that case we want to handle fluids. We can handle them in the micro scale, but in the micro scale, how do you put them on a chip? And this is exactly what microfluidics do. They try to miniaturize the liquid handling in a small microchip. So let's say let's have the example of a biosensor here. We have all the solid components in the microelectronic part of it, but in order to deliver the fluids and analyze them and sense them and do whatever you want with them, you need to have microfluidics. So some channels, let's say some hollow structures where you can pass your samples through over your electronics. So microfluidics has been around academically, let's say, for some years now. It's been almost 20-30 years. They have been in the labs all across the world, basically. People have tried to make them in different ways. So we've used glass, we've used silicon substrates like the microelectronics industry. We've used polymers like the DMS and various other polymers. In order to prove that we can have microfluidics and what they can do and how much functionality we can have with them, because when you go down to the micro scale, things change in the physics of fluids. And indeed, you will see here that we have made a lot of prototypes, all the research group working on this all over the world. But why don't you still know what microfluidics are? That's one of the issues puzzling most of the academics nowadays. Is okay, we're working on them, we're making papers on them, but nobody uses them. So there must be an issue there. So an expansion of why do we really want microfluidics is because what we want to do, our vision for the world, is miniaturizing the whole of a biomedical laboratory, which currently takes floors and whole rooms full with big equipment. We want to miniaturize all of that in small microchips, so that you don't have to go anymore, take your sample to a hospital and get it analyzed. You can just analyze it on the chip. In a way, in my mind, what we are trying to do is similar to what was done several decades ago with microelectronics, where you had big mainframe computers, but then when you had the integrated circuit invented, everything was shrunk down to a microprocessor. So how was this done? All of the integrated circuit components, the transistors, the diodes, the capacitors, were integrated now. They were not discrete components. And this is exactly what we are trying to do with Lab-on-chip. So take all of the discrete microcomponents that we already have working and put them all together in a Lab-on-chip. Here you can see several of the components that have been shown in literature around the world, some channels in glass and polymer substrates, some microballs and micropumps, micro-separators, micro-mixers, in order to help you mix the channels in the micro scale. A lot of technologies on chemical and biochemical detectors and sensors. Why do we want to do Lab-on-chip? because an analysis that you can do in a microscale will be lower cost than the analysis that you do in larger volumes. You will need a lot less reagents. You can have faster analysis because you can have parallelization of everything the same way you do with computers. You just have a lot of analysis at the same time. You can reduce the human errors because now you don't need lab technicians just pipetting your samples in there. Everything should be automated. So in one sentence, we can expect that such technology could save a lot of lives because you can take all of the analysis to every person in the world. So we have shown you all of these wonderful prototypes, but again, why haven't we seen anything in the market yet? And why isn't it as widespread as we would all imagine it to be? The truth is that we are lacking in good upscaling manufacturing technology. So all the prototypes that we've been making most of the prototypes have been manufactured with one of these technologies. So most of the academics have been working on CMOS technology because this is what we know. This is where we started, from integrated circuit technology, so clean room fabrication. But the problem is that despite the fact that we know it and all the prototypes work, the advantage of CMOS technology and integrated circuits is that they are small. That's why they're cheap. But when you want to handle something in real life, you can't have it cheap. That's small. So you need to have what we say chip-to-world interfacing. In order to have that kind of interfacing, the cost of the final device increases 10 times or 100 times, so it makes it unviable in realistic applications. Glass has shown some of the most of the commercial applications now, but they are mostly targeted for labs because they are extremely expensive. I mean, a chip, let's say 2 centimeters by 5 centimeters can cost up to 100 pounds. So apparently it's not something you would use in real life. Polymers are one of the good solutions because they are cheap. You can have an injection molded, you can do a lot of stuff with that. However, when you try to integrate electronics on polymers or metal groups or whatever more complex, let's say, again the cost becomes inviable for realistic applications. Recently, we have had some paper substrates shown, which are good until now. However, they are very recent, and so we have very few prototypes demonstrated, and we don't yet know how far they can go. So, what is the solution? We are all looking for something that can take these things large scale to everyone. So, how do we put everything together in a cost-effective way so to maintain this advantage? So what I've been working on for the past 6 years is putting everything on PCB. Why? I mean, it was first suggested in the 90s by some groups in Germany. However, because the focus at that point in the research community was not in putting everything together, it was basically to show that all the components can be done. So nobody focused on how to upscale. So it was sidelined by easier manufacturing methods like the glass technology or the polymers that were quite easy to be done. However, now that our main focus is on how to put them all together, PCB seems to be, I don't know, intuitive. Why? Because there is an industry out there, you guys. You seem to know very well what you're doing. And if you have the microfabrication capabilities that are currently existing in the industry are good enough for what you want to do, we may not be able to go down to nanometer scale, but for these applications we don't have to. I mean, 100 micrometers, 200 micrometers is good enough. And also, the integration of electronics is intuitive in this industry. So maybe this is the solution that we have all been looking for. So this is work that I've been doing before moving to the UK while I was in Greece 6 years ago. And we first tried to do what we call a micro PCR device. So when you do any kind of molecular diagnostics, for example, let's say to identify if you have a certain mutation in the gene that can cause cancer, the first step that you do now in the analysis is you take it to the lab, and in the lab you have a big piece of equipment called a thermocycler, which amplifies the DNA that you get out of any kind of biological sample that you have. This takes about 1 hour plus 1 hour for the analysis and consumes 200, 300 microliters minimum of the sample that you have to produce and the reagents, which are extremely expensive. What we did here with this chip is do the same thing, but the thermocycler does only in 10 minutes instead of an hour, and using 14 microliters of sample and PCR mixture. And here I can show that it works quite well. This is all done on flexible printed circuit board technology. When we started this project, our goal was not to use PCBs, we just wanted to make this chip. And intuitively, what we thought was just, we just take this substrate because it's there. But apparently, this doesn't make sense only to us. It's extremely good. Our next step was trying to integrate this amplification chip with a sensor on the same substrate. And again, we went for PCBs because they were there and they just made sense. So we had a silicon chip that is based on CMOS technology. We tried to put it together with a PCR in an FR4 substrate. We did it. It worked quite well, and this was actually made to fit in commercial instrumentation by a company that we were working with. But the problem with this was that you had to interface the CMOS chip into the PCB. And okay, I could do it in the lab. I made a good paper out of it, basically just injecting PDMS manually. However, if you want to sell this, you can't have 100 means just injecting PDMS. You need something that can be truly upscalable. And this is one of the things that puzzled me. So this is some work I've shown on sensors that can be into PCB. So you don't have to interface anymore CMOS substrate. You can just have the electrodes gold-plated, silver-plated, whatever plating is available in the PCB technology, and just use them for sensing. So in literature, you can see that several people have done DNA sensors on PCBs. They have done glucose sensors, they have done lactate sensors, so it's definitely something doable. Also, some very good collaborators of mine from Spain, they have been trying to do fluidic control on the PCB, so basically making valves and micropumps on PCB so that we can have everything on the same cartridge, on the same microchips. What I have been doing also when I moved to the UK in Southampton, which was a wonderful challenge for me, was to try to fabricate this time what I have tried to transfer what I've been doing in Greece, only this time with a commercial manufacturer, using only the equipment that Uber Electronics had, which was a partner here, the processes that they have so that we can have the minimum possible problems with adapting our technology to a commercial application. So the goal in this instance was to make some immunosensors, so point-of-care cartridges for tuberculosis, and have the whole thing, both the sensors and the microfluidics, in the same commercially fabricated microchip. Our idea was basically to use a multi-layer PCB concept. Why did we want to use multi-layer? Because for the microfluidics, we use dry film photoresist to form them, basically form hollow structures in one of the substrates, so it needs to be in one layer. We need gold plating pads to use as sensor pads, and we also need silver plated pads or vias in this case, to use them as reference electrodes, these are the necessary components to have a biosensor. And we did. Here you can see some fabulous prototypes that we did on PCB reference electrodes. Here you can see the wonderful PCB microfluidics that we have. And later on I can show you the sensing electrodes that we did. We tried a lot of different assays, and we successfully did. I won't get into too much detail of what it means because I think it's a bit out of scope. So here I show some pre-treatment I have to do to the electrodes, basically to bring them up to the cleanliness standard that we need for sensing. We successfully performed glucose sensing, immobilizing glucose oxidase in these sensors that I showed you before. We have successfully also tested interferon gamma, which is a biomarker for tuberculosis. Here I can show the results. The optical detection results are the results we get from the standard method benchmark in the clinical laboratory, and the electrochemical detection is what we did with the PCB sensors. Here I show a limit of detection that we were able to have with the chemical PCB sensors. There's still a lot of room for improvement, but it shows that in principle it can be done and it works. And then we moved on into integrating everything together in one chip, exploiting only the CAD software that is available, so that again that we try to change as little as possible, not use whatever we want. Here you can see the design of the final boards, all made in Outline Designer, no changes there. And we have 6 channels, 6, and we perform the whole class A, everything is done on the chip. The end here is a PCI Express connector, so the whole concept is just plug it in to the instrument that you want, make your measurement, and just take it away to concentrate. Here you can see the fabricated. You can see first layer, the silver-plated one, which will serve as the reference electrodes, the gold-plated part, and the microfluidics. Here you can see them all together and test the fluidic to see that they are. Because in microfluidics, what is extremely interesting and extremely difficult to get is to get everything completely sealed. We do not want to have leakages from one channel to the other because it messes up your analysis. And this is what we show here with the color dye, that we don't have any leakages. We use colors just to be able to see if there is any kind of leakage anywhere. So, I hope I have convinced you about this potential. We are trying to exploit this further. Here you can see a wonderful article that we had with the help of Philip, also in Newbury, on Lab-on-PCBs. There seems to be a lot of interest in this recently, both from the academic side and from the commercial side. There seems to be an opportunity here. We should all explore further. Yes, for the future, we are wondering if the industry will be as interested as it seems to be, and will help us, hopefully, to develop this further and get to some actual products. And yes, we are moving forward. We are also working with other manufacturers, in this case Steve. And I would like to thank you. That's it.
Any questions?
Are these are they for single use or continuous use?
Hopefully. The great thing would be if they could reduce maintenance because you reduce the cost. But if you are talking, it depends on the application that you want to do. If you want to do a medical analysis, it would be better if they could be disposed because you avoid any problems with cross-contamination from one sample to the other.
Any more questions? Good. What? Very interesting. Thank you very much.